Morning, Chair.
Morning, Srini. Slept well?
Yeah, Chair, feel a bit unwell today.
What happened?
I don't know why suddenly got headache today, Chair.
Cannot afford to cancel classes anymore. I think.
No. I'm not, teacher. I'm not. I
just let you know because we are behind already, too slow already.
Yeah, okay.
We may not be able to do all the past year paper. So it depends on you to ask question. Okay, anything you want to clarify before we carry on?
No, Chair.
Nothing to ask from your study.
No, Chair.
Okay. Let's carry on then. Let's finish it off.
Chapter 6.
Use the correct one now. Chapter 24.
Sorry, chapter 24.
Chapter 24. Okay, let's just review it before we look at the X-ray spectrum to refresh your memory. Right, this is your high voltage power supply. It causes this current to flow through, accelerate the current. So that's why the power is VI. Right, voltage is between 20 to 100 kilovolt. Provide a voltage across there or operating voltage V. Basically, the purpose is the electron is emitted by the filament or cathode. It's accelerated to the target. And this is a low power supply. It can be AC, can be DC, doesn't matter. Purpose is just to heat up the filament or cathode. Cathode is negatively charged. This is anode is positively charged. This is the anode. That's the target. So the electron emitter here will be accelerated by this potential to the target. So basically, control the filament current. Right? Control the current through the cathode and the current coming out here, which is given by that. Okay, so you want greater current, increase the voltage. So this electron accelerated, emitted by thermionic emission, accelerated to the anode, hit the target. So this current determines the intensity. Think as the intensity, each electron will produce an X-ray. More electron, more X-ray produced. Right? Think of the X-ray as photon. Each electron produce one X-ray. No, not more than that. One X-ray, one electron, one X-ray. More electron, more X-ray. So that affects the intensity. So at the target, the electron decelerate, give most of its energy to the anode, very little goes to X-ray. Right? 1% of the energy of electron appear as X-ray. You can see that 99% appear as heat. That's why we have to carry out the heat from the anode. If not, it will melt the anode. Then the electron is accelerated. So that is the work done. Right? Electron, the charge times the potential difference across the cathode and anode. So that's the maximum energy given by the electron to the target there. And this energy determines the maximum energy of the X-ray. That's the most it can give, no more than that. Since there's a lot of heat produced in the anode, you have to get rid of it by cooling this metal anode. Right? There are various ways of cooling it. So the energy, right? That is the energy given by the kinetic energy given by the electron to the target. So this is the photon or the X-ray that's produced. This Q is the energy given to the anode. Okay, so the kinetic energy of the electron, part is produce X-ray, part produce heat. And the minimum, right, minimum wavelength is where your Q equals 0, where you get maximum frequency lah. Okay, so I expect you next week, Friday or Saturday, focus 24, try this question. You will not be able to do all, since I'm trying to finish for you by next week, most of the topic, because we don't have much time already. Okay, X-ray spectrum. X-ray that emerge from the X-ray tube have a range of energies as shown in the X-ray spectra. We cannot look like a color light, right? This is absorption spectrum or continuous spectrum. We can view with our eye, but X-ray we cannot view with our eye. So that's why we view it differently. We have a detector to detect for us. That's the intensity, that's the wavelength. The spectrum consists of two components, namely the curve showing continuous distribution of wavelength with a sharp cutoff at short wavelength. Continuous frequency, continuous intensity at all wavelength, and then the cut off here, minimum wavelength. The other one is a series of high intensity spikes. That one, these are the spikes. These are the spikes. Characteristic of the target material. That means it depends on the target material you use. If you use tungsten, then it will show you that this is the emission spectrum of tungsten. Okay, so you can think of intensity as a number of photon of X-ray divided by time times the energy of the X-ray divided by the area, okay? Cross-sectional area. And that is your wavelength, that's the intensity. Okay, that's how we define rate of photons of specific energy emitted per unit time per unit area from the surface. Right? So there's a continuous distribution for all wavelength. How do we explain that? Accelerating electron can lose any amount of energy in the target. Right? When the electron hit the target, it doesn't have to lose all its energy. If it lose all its energy, then it produces this wavelength. So you can lose any amount of energy. That's why you have this continuous wavelength. Then you have a series of high intensity spike, right? Large intensity. Then you have the sharp cut off at short wavelength or minimum wavelength, or we call it maximum frequency here. How do we derive it? Where all the energy of the electron is form the X-ray photon. And then we replace our F by C divided by lambda. That's why we get this equation. Okay, be familiar. Sometimes it can be drawn this way. Instead of wavelength, this intensity, this is just your photon energy, energy of the photon, or it can be frequency of the photon. Same thing. Right? There will be a maximum frequency or maximum energy. And then the spike will be here. Right? Remember the kinetic energy of this electron is given by that. That's the maximum we can get. E times V. And that's your X-ray photon that's coming out. So that is that kinetic energy converted to your maximum frequency here.
Teacher,
Yep.
the WhatsApp is showing that you're recording some audio or something, teacher.
Ah.
Yeah.
Oh, thank you. Let me check what is happening. Are you seeing anything?
I saw like the green thing recording audio. Now, since when I say only, then it stopped already. What was that, teacher?
Not sure. Let me just check what is happening.
They're now coming also recording audio.
Okay, are you seeing the slide?
Yeah, I'm seeing the slide, sir.
Okay then. Okay, let's explain the continuous spectrum. I already explained to you, I'll summarize for you. When an electron strikes the anode, it will be attracted towards the nucleus of an atom and nucleus. This will cause it to change both speed and direction. So when it changes speed and change direction, it decelerates. Right? That's what happened. This electron that is accelerated coming in, attracted by the nucleus. Then as it decelerates, X-ray is given out. So that explains the continuous spectrum. Right? It doesn't have to be always there. It can be nearer, or it can be further. That's to explain the continuous spectrum of intensity. A decelerating electron loses energy by emitting electromagnetic radiation. Okay, and that X-ray we call breaking radiation. Energy given by electron, I just review with you. Right, that's the maximum kinetic energy. When the high speed electrons strike the metal target, as a metal target, large deceleration occur, and the radiation produced is in the X-ray region of the electromagnetic spectrum. So because of the deceleration of the target, the X-ray is produced. Since the electron have a continuous distribution of acceleration, right, can have different acceleration, so it can give different amount of energy to the target. That is, they can give any amount of energy, right? They can give all the energy, or they can give different amount. Cannot give more than the maximum. So they explain the continuous spectrum on different wavelength. Okay. Right? That one can that produce the X-ray. There's a maximum kinetic energy of electron. There is a energy given to the target. And when Q is 0, then we get that is your maximum frequency or minimum wavelength. Okay, now we explain the cutoff wavelength. Right? Same, maximum kinetic energy of the electron or the work done by the accelerating potential. Then take our H down, we get our maximum frequency. Then replace our F, right? F is C over lambda. Right? C over lambda. Then lambda take across there, H take it out, EV take it down. That's how we get this equation. Cutoff wavelength is the minimum wavelength of X-ray emitted at a particular operating voltage. This corresponds to the maximum energy given. That's the maximum energy that the electron can give. Maximum kinetic energy. Minimum. So that minimum depends on the accelerating voltage. Accelerating voltage increase, minimum will be smaller. At cutoff wavelength, the whole of the energy of the electron is converted to energy of photon. Okay, I'm just repeating, that's all. In case you can't see the conversion, right? Take this up, take this one down. Okay, so that's why it's saying the higher the energy of the electron, that means the higher this accelerating voltage or higher energy, then this will be the smallest wavelength, shorter wavelength. Okay, try calculating this one, number 11 in your worksheet. An X-ray tube operated at a DC potential difference of 30 kilovolt. What is the minimum wavelength of X-ray emitted? Okay, calculate for me. Just using this formula. Got the answer? Yep, got the answer.
Yeah, I got the answer. It's 4.14 times 10 to the power negative 11.
Okay, good. It's one of the few times that I get it correctly. Good. Okay, I think we won't bother to summarize that already. We have completed already. Okay, let's explain the sharp spike. Right, minimum wavelength we have explained. Higher voltage, higher, the curve will be higher. The spike will still be the same. Sharp spikes are high intensity peak, consists of group of 2 or 3 peaks of high intensity radiation superimposed on a continuous spectrum. Right, we give it different name. Right, this is from the K shell, so we call it K alpha, K beta, same like here, L shell. The spike doesn't change, where the accelerating voltage is increased, the spike still stay in the same place because the characteristic of the target. Only the intensity curve becomes higher because more energy given, more energy for the intensity. Location, that is the wavelength of the spike, depends on material of the target or characteristic of the target material. Different material will give you different wavelength for the spike. For a particular material, as the voltage is increased, the location of the peak remains at the same wavelength. Right? It doesn't change. The wavelength is still the same. The peak at same wavelength. Okay, so that's how it varies. Only at certain voltage you will see the spike. At lower voltage, you won't see the spike. Also depend on the material. Right? Occur when operating voltage above certain value. So for this particular target, above 20, then you can see the spike there. Okay, I think we won't repeat itself. Let's try to. For the spike to appear on the curve, the operating voltage must be sufficiently high. Example for tungsten, the operating voltage must be greater than 72.8 kilovolt. Right? Let's explain the cause of the spike. Right? The picture I explained to you. This is the alpha. That one there. That one will cause a K beta. That one. Okay. That means the X-ray is produced by electron transition from a L to K, M, K. Right? M shell, L shell, K shell. So there are peaks. These are peaks corresponding to emission line spectrum. So these are emission line spectrum that we cannot see. We see as spikes of atoms of the target. The electrons that bombard the target knock out the inner shell electron. Right? That's the inner shell. You knock it out. Then the electron from outer shell must come down and replace it. So that's where the X-ray is produced. And the subsequent de-excitation of the electron from the nearby shell gives rise to the line spectrum. Okay. This is a poor drawing now. Right? Just to give you some idea. That's your alpha, that's your beta. So that's your alpha, that's your beta. Any comment or anything not clear?
Okay.
Basically, your electron knockout, the electron coming in, accelerated electron coming in, knock out the inner electron, then electron from the L shell come down, produce the alpha, K alpha X-ray. Then if the electron is from the M shell, filling out the K shell, then you get your K beta X-ray. You just identify that's all. A different X-ray there, a different spike. Okay,
Okay.
Okay, I don't think we will summarize for you already. We have summarized enough already. It's just repeating. Anything you want to ask? Anything that is not clear, you want to clarify?
No, sir.
Okay, I think we have finished everything already. These are you can draw your own table to summarize. Okay, let's go to X-ray diffraction, page 245 in your book. Right, we have done this earlier, where the X-ray tube, there's your LED screen. You have basically this is your collimator if you like. You want a narrow beam coming out. And then there's your crystal. And then on the screen there, we can see the diffraction pattern. This is your crystal. To produce diffraction pattern, remember the spacing of the slits, right? That's spacing. On the diffraction, we cannot, the spacing of the slits on the diffraction grating must be of the order of the X-ray. So we cannot use diffraction grating because X-ray is a smaller wavelength. So no diffraction, very little diffraction occur. So that's why we have to use, so ordinary diffraction grating cannot be used as the spacing of the slits are greater than the wavelength of X-ray. So the diffraction grating that we must use will be crystal, right? Where the distance between the plane are of the order of the wavelength. A regular crystal consists of an ordered array of atoms can be used. The distance between the atoms is of the order of the wavelength, right? So that distance there is of the order of the wavelength. So that crystal plane can be used as your diffraction grating. X-ray directed towards a crystal produce waves of different phase which combine and undergo destructive interference. X-ray traveling in certain direction will interfere constructively, producing observable diffraction pattern. Okay, let's look at this particular one. This is your three crystal plane, the plane there. There's a distance between the plane D, distance between the plane D. There's an incident ray coming in. Right? AD, this one, AD. BC, there's a BC, incident of plane at glancing angle. Instead of using angle of incident, we use glancing angle. Glancing angle, we call this glancing angle. The angle is made with the incident ray made with the plane, right? Which is the same as this one, theta. So this is also theta because the angle of incident equals the angle of reflection. So these two angles must be the same. Theta is called the glancing angle or Bragg's angle. AD and BC, right? Same wavefront. And then DF and EG. DF equals to EG, right? They have the same travel distance, the wave. For the two rays that are in phase, this AD and BC are in phase. We want constructive interference, right? That ray there, BC, have to travel that extra distance, right? That extra distance. So if you want the constructive interference to occur here between F and G, then it must have a whole wavelength. The N is whole wavelength, 1, 2, 3. So it means that the path difference CP and PE must be equal to N times lambda. Right? Lambda is your wavelength of X-ray. Okay, that's what we have said. So that is a triangle, right? Which is the same as here. I just take it up here. There's your D. There's your angle theta. This is your angle theta also. Okay, that's 90. So that one plus that one is 90. So that's why this one equals to that angle theta. So that CP, right? That's your D. Is D sine theta further away from this angle. Right? That CP there and PE are the same. So both of them are equal to d sine theta. So we add these two together, we get 2 sine theta equals to n lambda. So this is a separation between the atomic plane. This equation is known as Brett's equation. Okay, anything that's not clear?
Okay, so that means DC is equals to, I mean, D, and then C is equals to the E and D, right? Am I right? And then later you get the sine theta one. The theta is known as the Bragg's angle, something like, right? So yeah.
Theta, that theta,
Bragg's angle.
right? We call it glancing angle. Since this is the one that the person came up with, we call it by his name, Bragg's angle. Rather than use angle incident and angle reflection, we call this angle Bragg's angle. Right? The angle made with the plane.
Okay.
These two have the same path difference, AD and BC. Okay, but it has to travel extra distance here and extra distance here, and then EG and DF have the same path difference. Right, so this extra path difference is given by this. And then we try to write this path difference in terms of the distance between the plane. That's what we are doing here. Okay.
Okay.
Measurement. Right, this is your X-ray. This is your detector. This is your normal to surface. That's your Bragg's angle. Right, remember that can go straight. So this angle is theta. This angle is theta. So this angle is 2 theta. So we can shift the detector here, right? Incident ray. And then after that, we can turn it to 2 theta to detect the X-ray. X-ray spectrometer is used to measure the separation between the atomic plane in the crystal. Collimators are used to produce parallel beam of incident X-ray, which strike the crystal at glancing angle of theta. Right? That's your glancing angle theta. We don't want a wide beam of X-ray. Right? That's the purpose of collimator, a small hole to limit the size of the beam. Detector detects the X-ray. That's the purpose of a detector. We cannot use our eye, so we have to use a detector. Both the crystal and the detector can be rotated so as to measure the glancing angle. Right? And rotate this one from here to there, or I can rotate this one. Right? That detail is not important to us, just for the scientists who are doing the measurement. Okay, so we have summarized that all these equations that you need to know for X-ray. As you need to know what is continuous spectrum, what is pi, and then Brett's equation. That's your Brett's equation. Okay, and they need to know also all these equations. Okay, I think let us finish nanoscience and then do some
Then
questions.
go to chapter 25.
That's the next hour. We want to do some
Okay.
questions first. Make sure you understand how to calculate, because your exam is mainly calculation. Explain the basic concept of nanoscience. State the application of nanoscience in electronic devices. Right? This is I don't know whether you have seen that or not. Right? Where you use a very big tube. Right? These are like transistors, but we call it valve, made of glass. That's why it's so huge compared to during the 90s or 80s, getting smaller, and now we get smaller still. Right? So now these are discrete components, this one. And these are your IC. We are going to smaller and smaller. Right? Going for electronic. Okay, nanoscale, how big? That's your nanoscale. Right? Nano is 10 to the power minus 9 meter. So as long as it's between 10 to 100 nanometer, then it's nanoscale. right? That give you the size of a piece of paper is 100,000 nanometer. Human hair is 80,000 nanometer. DNA is about 2.5 nanometer. Nanoscience is a study of properties of structure of size smaller than several 100 nanometer. It's about nanometer, 100 nanometer. Object on the scale of nanometer study in nanoscience include atoms and molecules. One of the aim of nanoscience is to study how to manipulate and control chemical and biological matter on a small scale. Right? The advantage of nanoparticles have enormous surface to weight ratio. Right? Different from macroscopic property. When we look at the whole thing there, the surface is smaller, the weight is larger. That's why I mean by surface area to weight ratio. Many nanomaterials have special properties that differ from the parent bulk material. Right? That means if you look at copper at nanoparticles and copper as a element, the properties completely different. Okay, so that's summarized for you. We are more interested in this area. Computer, electronic devices, thin film. Okay, these are other areas of interest. I think your book gives quite a fair bit. Nanotechnology in electronics. Nanotechnology is used in many communication, computing, and electronic application. That's why your laptop becomes lighter and lighter compared to many years ago. It provides faster, smaller, and more portable. That means you can carry around. Right? Portable means can carry around, not too heavy. This system can manage and store larger and larger amount of information. Right? Consider my time where we want to use telephone. That time is very expensive. Only certain people can afford to loan telephone, and you want to make a phone call to Taipei. We have to tell them first that what time we want to call. Then we call, and operator will tell you your 10 minutes is gone. You better hold up, or now I'll cut it off. Right now we take it for granted. We can make telephone call anytime we want, or now better still, we got our smartphone to make phone call. Right? You can see the change in technology. The system can manage and store larger. That's what it means, store larger and larger amount of information. Nanoelectronic means using nanotechnology in electronic component. There are many applications such as computing and electronic product, including flash memory chip for iPod, nano antimicrobial and antibacterial coating on mouse, the keyboard, and a cell phone. Aim of nanoelectronics is to process, transmit, and store information, taking advantage of the properties of material that are distinctly different from macroscopic property. Right? Macroscopic property is what you can see, very large. Right? So we are looking for nano transistor, nano diode, and organic light emitting diode. Nanotechnology is used for printer electronic, for RFI smart card, smart packaging. It is used for more like a video game and flexible display for ebook readers. Nanotechnology is used for nanoscale transistors that are faster, more powerful, and increasingly energy efficient. You will see soon that your computer entire memory may be stored on a single tiny chip. You want to read more, you can go to that. RFID is your radio frequency identification. Right? We are now using it in car, touch and go, right? Highway, being told uses electromagnetic field to automatically identify and track tags attached to object. An RFI system consists of a tiny radio transponder, radio transmit receiver, and transmitter. So basically, it has to have a reader. You have to stand out radio wave, then you have the, identify the tag, and then you have to be a receiver, right? Transmitter and receiver. Then identify the car, then you can make payment. When triggered by an electromagnetic interrogation pulse from a nearby RFI, that is attached to your car, reader device, the tag transmit digital data using an identifying inventory number back to the reader. This number can be used to track inventory goods. Right? So your car will have a tag, RFID tag. Right? There's a number or a code. Then the reflector pulse will take this code from your car and then send it to the reader. Right? That's how you pay for your toll. Okay, I think we have completed. Let's try some questions before we stop for a while. Okay. We have to speed up already. Try to finish as soon as possible. Okay, focus 24. Objective 1 to 26. Make sure you try that out for next week. May not do all. Depending on how much time we have. I think we should finish by next week already.
The entire syllabus, sir.
Yeah.
Okay.
After that, we don't have much time already. So we will have to do selected question in the past year paper. So you will probably have to tell me what question you want me to solve earlier. I only completed one topic, oscillation. Okay, try this question. 24.7. This one. Energy level for K, L, and M. Shell of silver is listed. Determine the wavelength of K alpha, K beta peak when electrons strike the silver target in the X-ray tube. Right? K means K shell. So first, either give a sketch of the energy level of the shell or energy level. Right? Should be able to draw the energy level, something like that. The more negative is always the lowest one. Right? That's a K shell. That's an L shell. That's your M shell. Then give you energy. Then you can imagine how to calculate. Okay, determine the wavelength of a K alpha. This one. And K beta is this one. I've given you the equation. Can any problem? Let me know if you have problem calculating.
So I'm not sure what the lambda is, teacher.
Okay, lambda. Energy is given. Right? M plus 1, M plus 1. N is this one. Then use this equation, that's all.
9.06 times 10 to the power -7.
No? What went wrong again? Where did you go wrong? You have to subtract. That is always possible.
Yeah, I straight away put that E inside the down one. I never changed the
Convert it to
21.95.
Joule first. Convert it to Joule first. Then put it inside.
I never converted to Joule. I straight away divided it with 21.95.
Very careless, very careless. Cannot afford the carelessness. Okay, try the other one. J beta. Same step. They say you get different answer, that's all.
Wait, Archer, wait. 4.98 times 10 to the power of -8.
Okay, good. Try number 2. Graph show the intensity against wavelength for X-ray produced from the X-ray tube. Find the potential difference between the anode and cathode, which will produce the above graph. Sketch the X-ray spectrum obtained if the potential difference between the anode and the cathode is greater than the value in A. Label the spectrum Q. Okay. How to calculate? What formula to use?
Sure.
Yeah.
Just want to ask maybe can have the the replacement supposed to have, can have it like extra class next week, Monday and Tuesday. Finish the whole thing like you said instead of Saturday. So Friday, Saturday also will have the thing lah, but like finish fast lah.
You got the time or not?
Got, like after school finish, maybe 3:30 can answer. 3:30.
Monday 3:30, Tuesday 3:30.
Yes. Because I finish school at 2, then by the time finish everything will be like 3:30, then you can have the class.
Are you sure? You are so tired already. How to concentrate? Well,
No, I'm okay, Che.
We can try and see. If you cannot, then Tuesday we can cancel.
Yeah, okay, try and see. Monday lah, Che. Monday.
Okay, you try
Okay.
Monday and see. 3:30, okay?
3:30.
Okay, how to calculate? What formula to use?
Lambda equals to HC over EV, so V equals to HC over E lambda.
Right, the accelerating voltage equals to your photon energy. That one?
Yeah, that one.
Then calculate out. Good. See whether you can get it correctly or not.
Uh, 2.39 times 10 to the power of 3.
Okay, good. So your graph, how does it look like? Where is the cutoff wavelength? Shorter or longer?
Shorter.
Where is the spike?
Below.
spike? Is this same wavelength, lower wavelength, higher wavelength?
Higher wavelength.
How about the continuous curve?
Not sure, Che.
Not paying attention. The spike should be the same because it's the emission spectrum of the target. You use the same target, you get the same spike. Continuous spectrum will be higher. Right? Spike is the same wavelength. Because it depends on the target material. Higher power, this is higher power. Right? Shorter wavelength. Okay.
Okay.
And number 3.
Teacher, Che, the break, right, Che, are we taking like half an hour or just 1 hour, 1 hour, Che?
Break is only 5 minutes. Why we want to take 1 hour for what?
No. What I mean is because every time the video, you like every time half an hour class, then 5 minutes
This one I'm
break.
going to finish in 1 hour's time.
Oh, okay. That's all I asked.
So I'm going to do some exercise with you. After that, we will stop.
Yeah, okay, sure.
5 minutes break because we don't want the video to be too long.
Yeah, okay.
Too long also difficult for you when you want to revise. After that, we go to a new topic already.
Yeah, can.
Okay, explain the continuous spectrum. Yeah. Why do we get a continuous spectrum? Yep.
How do you get the continuous spectrum?
It's the electron coming from the being accelerated from the filament hitting the target. So how do you explain the continuous spectrum?
Okay, continuous X-ray spectrum is produced when the fast-moving electron from the cathode are decelerated and hitting the target anode. Different electrons convert different amount of their kinetic energy into X-ray photon of different wavelength, resulting in continuous spectrum.
Okay, the electron coming in has maximum kinetic energy, but when it hits the target, it can lose different amount of energy and then produce X-ray at different wavelength. So they explain the continuous spectrum. How about the characteristic X-ray spectrum? That means the spike, the sharp spikes.
The sharp spikes. The characteristic X-ray spectrum is a result of the electron from the cathode knocking out shell electron from the target atom. When the vacant shell are refilled by free electron, X-ray photon of specific wavelength are emitted.
Okay, I think this one, your book is a bit wrong. Right?
Okay.
Characteristic X-ray spectrum is the result of electron from the cathode knocking out inner shell electron from the target atoms. When vacant shell are refilled by electrons from outer shell, X-ray photon of specific wavelength are emitted. Okay. Minimum, how do you explain the minimum wavelength?
Minimum wavelength occurs when all energy of the accelerated electron is converted into X-ray photon in single collision.
Okay, looks like something wrong with my computer. Somebody is changing my you can see that.
There, the one down.
I know. Somebody is changing my thing. Looks like some virus or something. Always.
Maybe hacking lah. Maybe somebody hacked or something. I don't know.
That's why I suspect. right? When all the energy of all the kinetic energy of the electron is given to produce the X-ray. Okay, the others you can do yourself. Let's try the next 24.8.
Okay.
Try this one.
They want what wavelength? So HC over EV lah. Sure. Wait, so 1 minute. (3.55 times 10 to the power of -11 meter.
A formula to use.
HC over EV. Yeah.
Okay. Try number 2. We are getting better already. Good. Electron in X-ray tube are accelerated to a potential difference of 40 kilovolt towards a target. As a result, 600 joule of thermal energy is produced per second. However, only 1% of the energy supplied by the electron is converted into X-ray. Find the average rate at which the electron strike the target. This is a challenging one. Right? Work with the information that's given. Right? This 60 joule is your power, right, per second. It's 99%. And then that one there is a setting voltage. So you have to calculate the power supply. And after that, can find the current. Yeah. Right? Power loss as thermal energy. Write it down. Can? Any problem? Write down step by step what is given. Then you can think of the formula to solve. Right? Power supply equals to rate of thermal energy produced plus X-ray energy produced per second. Right? In formula form. Can or not? Can or not? Any problem?
No, that means 100 over 99 times 600. Then you get equals to IV lah, teacher. Sure.
Yeah.
The physics, right? Do they ask more to explanation compared to calculation or more to calculation?
I think yours is mainly calculation.
Oh,
Explanation.
thank God.
Do have also. You can see
No,
from all
but
your exam. I can see from all your exam. Mainly, is it mainly calculation or mainly explanation? There are both.
oh,
But
okay.
I think it's towards more of calculation.
Yes. Okay.
So can calculate. Right? Calculate the power supply.
Power supply, 9.47 times 10 to the power of 16.
Okay. Anything not clear? Anything you want to comment?
1 minute, sir.
First, calculate the power supply.
Okay.
Then this one is basically power supply, produce a number per unit time times E. E is your energy of the electron. Or just times your V times current, no? Current times V, no? Same thing. Right? You don't want to work with E, you can use current times V, and then current is this one. Same thing. Okay, if you are all right, let's do one last question. Anything that is not clear? Write down step by step. Then you can calculate out. I initially also got lost. Understand the question. That's the most important thing. Okay,
Okay, sir. That means all practice only lah, sir.
I think you can try 24.9.
On my own.
State the few possible benefit of nanoscience.
Stronger and lighter material, faster computer, higher efficiency on solar energy conversion.
That's all. Right? Any of these things? Memory word, that's all. Nothing else. Stronger and lighter material, motors on molecular scale, faster computer, more efficient catalyst, high efficiency of solar energy conversion. Right? Increase storing capacity, faster also. Okay, anything else you want to ask? If not, we'll take 5 minutes break. And then
sir.
start a new topic. Give you a short break to refresh yourself and go for a drink if you want.
All good, sir. Wait, sir.
Yeah.
I think I can still pass that, sir.
It's really up to you. Right? I can be honest with you. You are practicing hit or miss. What does it mean? It means that if what you study come out, you will pass. If what you study didn't come out, you will fail. So it's really up to you how much work you put in. I tried my best to help you, but so far you are the one who are not doing your homework. Okay?
Okay.
So it's better for you to put in the effort and ask questions. Whatever you don't know, you ask.
Okay.
Okay? If you are okay, we will stop here.
Okay, sir.